as you mentioned earlier, Dr. Hughes's book being part of the essentially the theory manual for Maestro, there are basically three textbooks that sort of define the theory manual, which is his original textbook, the Ship Structural Analysis and Design by Hughes and Paik, as well as the Ultimate Limit State Design of Steel Plated Structures. So I guess the internal Maestro limit states that we mentioned earlier, if we start looking at the strength assessment aspects of Maestro, those are defined in ship structural design. And for things like panels, for the stiffeners and or the plates, some of the various criteria that are implemented within Maestro are for collapse of stiffener flexure, stiffener tripping, combined buckling, and membrane yield. For the stiffener plate combination, or stiffener plate yield rather, you have it for both plate and flange. And for plate, you can evaluate local buckling. For the beams, for specifically girders and frames, we evaluate collapse with girder and frame tripping, as well as compression flange of the flange and plate, and yield for flange plate and plastic hinge. One of the other limit states that's implemented in Maestro is the Alps-Allsop theory. This was, I guess, based on the work of John Paik. Some of the various modes that are covered for evaluation in Maestro are illustrated graphically in this slide. Another one we mentioned earlier was the U.S. Navy methods, the naval vessel rules. Now this one is subject to distribution D, so it is a separate module. You'll see it in the interface in Maestro, but it's installed as a separate module. So it's, I guess, a more limited distribution. But again, all of these criteria, when you apply these limit states, it does evaluate, everything within the entire vessel. You can see basically, what some of these patches might look like for evaluations within the hull in here. So I guess when Maestro goes to apply the limit states here, it does a very complete assessment through the entire hull. It'll evaluate for both yielding and buckling. It looks at every defined loading condition in your model. So even though typically the way Maestro runs, you create one model based on the original scantlings, but you can have as many different loading conditions as you want defined in there, whether those loading conditions are from static wave, different loadout conditions, or all the combinations of them, as well as the results from something like your Maestro Wave extreme load analysis results for your lifetime exposures. So you can have tens or even hundreds of load conditions if you want. Maestro will automatically evaluate all of them. And when you go to review in the post-processing options, you can evaluate just a single load case that was run, or present the results for a single load case, or you can say, I want to see the worst of all of them. And it'll basically show you a composite across the entire vessel for the worst case of, or each element will present, I guess, the worst case of all available loading conditions. And as we mentioned earlier, I guess you can use different factors of safety. Or the user can adjust the various safety factors. Although typically the default values are left untouched. So as we mentioned earlier, for some of the criteria, you may need to find out what the defines a stiffened panel within Maestro. Rather than the user having to define what those stiffened panels are, Maestro will automatically search the entire vessel and define what the bounds of a stiffened panel are. So this search is done automatically, and it basically helps to define what the true boundary is of a given stiffened plate. So you can see here with dynamic query, when we're looking at and these are called evaluation patches. So here is, we're looking at patch 445 within this model. They're all color coded, so you can see the extents of each individual evaluation patch. But when we look at this panel, it tells us what the length, width, thickness, and the number of internal stiffeners are. So while not shown here by the red lines, there are embedded stiffeners within this plate. Similarly, we do the same thing for the frames and girders. So when you're looking at a beam, and actually this is an older graphic, the current implementation of Maestro will not only show, I guess, what is defined for the beam patch, but also it'll show on the plating what the supported amount of plate is, as well as the effective amount of plate that's attached to the beam. So you'll see a couple of additional lines on the plating showing the extents of what that beam is supporting. With regards to evaluating the final results, one of the nice things is that you can visually assess the entire model. You get color-coded results for, say, stresses or deformation or whatever across the entire vessel. And you can view the vessel both in the original state or in its deformed state, and you can control what the amplification factor is on that deformation if you want to sort of exaggerate some of the deformations to better visualize what exactly is going on. But then once you look at the model with the color-coded results, then you can also go in with a dynamic query to get the detailed numerical values associated with the results. Similarly, you can control some of this information, such as showing only the members that fail. Like here, you can see anything in gray past the criteria being evaluated, whereas only the values that are associated with the color on the results bar show values that were insufficient, and the color indicating by how much. And as we mentioned earlier with the dynamic query, you can, in this case, rather than recovering stresses, you can recover I guess what are referred to in Maestro as adequacy parameters, and it sort of non-dimensionalizes the results from a scale of -1 to 1, since if something fails, you could have values going up to infinity, but Maestro uses this adequacy parameter to sort of non-dimensionalize the results so that everything falls within a scale from -1. Anything below 0 is failing, and anything above 1 or above 0 is passing. And if you're exactly at 0, then your element just meets the criteria. So Maestro also has implemented the hull girder ultimate strength. Now this, when a vessel fails to this degree, it's not a simple binary pass-fail. It's more of a progressive failure, so that when a ship starts to fail and portions of it buckle, the hull can still, I guess, withstand additional loading, and the failures will eventually compound till eventually you have a full failure. But this is well beyond simple beam theory. And when running, I guess, this hull girder ultimate strength, I guess this theory will take into account that all of the multiple local failures and incorporate them into the overall system. The hull girder ultimate strength in here can use a number of different load patterns in here, and some of which, and you can use more than one, but you can use any combination of the vertical bending, horizontal bending, vertical shear, horizontal shear, torsion, and panel pressures in this analysis. So here's a simple plot of a section, and if we look at the progressive collapse of this, you can see by the color coding exactly where things are starting to fail as you run through the increased load. Just do another quick pass through that. But this was using this third scale frigate model, and this was compared to some experimental results, and you can see there's quite good agreement between the computational results and the experimental.